So today we're going to talk about guidelines to help you make graphs this year in chemistry as needed, and making this a video so that you can pause it, you can go back to it and look at it, so that when you have graphing assignments, you can make the best possible graphs, as well as this can be a resource for you. So let's get started. For intensive purposes, typically in science, we're going to make a line graph, okay? Other graphs types that you may have learned, like a bar chart or a pie chart, just really aren't practical. Here are some of the reasons why we're going to use a line graph. Okay, bar graphs typically look to show how a single quantity varies with time, or how it's compared to other quantities. Of all the other types of graphs that you could make, this would probably be the second most common. However, we're really going to be comparing how one variable changes relative to another. And so for bar graphs, like, if you were trying to compare, like, what's everyone in this class's favorite color, and then you got everyone's data and you were comparing, like, favorite color, amount of people, stuff like that. Well, okay, if you were collecting that type of data, then yeah, bar graph would be appropriate, but otherwise it would not. Pie charts, while you do see them in scientific literature, I can't think of a time this year you're going to be using them, but they're good to know what they are. You just won't likely be making them. The reason we're going to be using line graphs is because we're going to be looking at how does one variable, how is it related to another variable. So we really, when we do experiments this year, we're going to try and isolate two variables and look at, if we change one, how is the other one affected. And so that's what we're really all about, and that's what we're going to be doing. Okay. As a note and as a refresher, the x-axis is always your independent variable. That's your horizontal axis. That is what you change. And the y-axis is the dependent variable. It's what got changed. Okay, so if you're comparing temperature versus time, so you're heating, say you're heating a cup of water, you're going to be looking at how, as I change the time, okay, how does the temperature change? So time would be your independent variable. That's what you're changing. You're letting time, pass. And then you're going to see how does the temperature change with that. And maybe you're heating or cooling something, but that would be a very simplistic example. So in other words, your y variable, your vertical axis changes as a result of x, not the other way around. I think this little example is helpful for some students when you're thinking about age and height. Okay, your height changes as a result of your increasing age, not the other way around. You don't age because you get taller. You get taller because you age. So age would be your independent variable, and your height would be your dependent. Height is dependent on age, not the other way around. I don't want to see a connect the dot series. Okay, graphs should be shown as lines or curves. There are a few exceptions to this again, but for the majority of the time you're going to be doing a best fit line. Okay, so here's kind of an example. If this was your data set, okay, I would not want you to connect the dots to every data point. All right, in general, this data right here is showing an upward trend, but you would show that as a straight line here. Okay, so you can notice that this line right here, it's not touching all of the data points. However, it's showing the general increasing, whatever these variables are. This is just a very basic graph, showing as one goes up, the other goes up in a general manner. Okay, I'm going to show you some examples on if it's going to be a straight line or a curve. You kind of really just have to examine your data. This is probably the most common mistake that I see students make, and I'm trying to have you unlearn something that perhaps past science teachers have taught you. But the line that you draw doesn't need to start at the origin of 0, 0. You really have to examine your data to know where you're going to start your X and Y axis. You may want to star this, write this down, bold it in your notes, okay? Because a lot of students think, oh, I have to start my graph at 0, 0, and then they have no idea how to fit in all their data by starting there, okay? So an example, if you make a chart, okay, of the effect of a baby's weight on age, you wouldn't say that a baby weighs 0 pounds when it was born, okay? When you're born, you do not weigh nothing, okay? If you weighed nothing, you would not have been born, okay? So it might not make sense to start your graph at 0, 0. I'm going to show you a couple examples of data sets. So typically when you're graphing, you have some kind of data and thinking about where you'd want to start this graph. So if I was going to plot this data right here, so you're looking at an amount of some salt, okay, and it's in milliliters versus the temperature. So some amount of salt is changing the temperature. You're starting at 50 milliliters, you're decreasing to 15, and your temperature range starts at 22 and goes to 36. So in neither one of these cases does it make sense to start your graph at 0, 0. So if I was plotting this, one, I'm assuming that the amount is affecting the temperature. Okay, so this is going to be what I'm changing, and this is what's going to be dependent on it. Typically, temperature is typically your x-axis, but in this case, it's going to be your y. So I would probably start. So my lowest point is 15. So I'd probably start at 15 on the x-axis and go up by increments of 5, okay, to fill the space. And my temperature, again, I'm not going to start at 0 because my lowest temperature is 22. I'm probably going to start at around 20 and then end my y-axis around 40, okay? So whatever my data set is, that's where I'm going to start my x and y-axis. They do not need to start at the same point, okay? You want to start where your data starts and you want to end where your data ends on both your x and your y-axis. For this one, okay, you start with 10 and go to 30. Now I'm assuming if you started at 0, the pH would be 0. This one might make sense because also this other value, this is going to be your x-axis, and this is going to be your y. Okay. This one might make sense to start at 0, 0 and then plot your data because the numbers are close to that. But your x-axis should end at like 30 versus your y-axis should end probably close to 12. Okay, because that's where your data ends. You have to look at that. And I'll show you a couple graphs that show, like, they obviously had some data. This one is plotting absorbance versus concentration, and this one starts at 0, 0, probably because when the concentration was 0, absorbance was 0. And you look at when you had an absorbance of 0.1, okay, like these you can see the data points were really close to 0, so they had very small concentrations, very small absorbances. It made sense. But the scale on this one compared to this one, they are not the same, and they go to different endpoints. This one ends at 0.6 versus 200. So I want you to note that that this person is plotting what their data is giving them versus this data, okay. It has negative values. It's starting at negative 6.5, going to negative 9.0, okay? And it's going from 3.10 to 3.35, a very narrow range. But you can see they're plotting the numbers that their data has given them, okay? That's the most important part that I cannot emphasize enough. So I hope these examples help you in seeing you got to plot what your data gives you, not just start it at 0, 0, because that's what you've been told in the past. All right, let's talk about how the title of a scientific graph should be. This is something you want to make sure you're doing correctly, okay? A title of a graph should be the dependence of your dependent variable, your y-axis, on or versus your independent variable, your x-axis. Remember, y-axis is your vertical axis and your x-axis is your horizontal axis. So a couple examples. So if I was plotting pressure versus temperature, the title of my graph would be the dependence of pressure on temperature, because pressure changes because of temperature, not the other way around. So this is my y-axis. Oh, didn't mean to have that pen. Anyway, this is my y-axis versus my x-axis. So the title actually tells you which variable is which. Okay, so temperature should be on the x-axis and pressure on the y. Okay, the example I gave with a baby's weight versus age. Remember, weight is dependent on age, so the dependence of weight versus age. So you notice it's just on or versus. This is the correct way to title a scientific graph. If you really look at graph titles in the literature, you will see that it's the dependence of one variable affecting another. So how does your y-axis change relative to your x? Other points. You must show units on both axes of the graph. So do you have time? Time in what? Seconds, minutes, hours, decades, centuries? I don't know if you don't label it. You always must have units. So whatever they are, make sure they're labeled. And if they're not made clear, then I don't know what I'm looking at. You don't know what you're looking at, okay? I've kind of talked about this, but I want to make sure it's in this. You need to fill the space. Whatever your graph paper is, you need to scale your data to fill the space. I don't want these tiny little graphs in this huge sheet of graph paper, okay? So you want to make sure you're spacing it. That can honestly take the most time is figuring out, okay, your scale. So like if I go back to this slide, okay, if this was the data, you know, figuring out I have to go up by 0.1 on my y-axis. I have to go up by 50 because this filled the graph area. This one, I need to go up by 0.5 and over by 0.05, okay, and scaling it to fill the space. Make sure you're looking at your data to do that. And when you're drawing your best fit line, use a ruler or straight edge of some kind, of bookend, something to draw a straight line so it doesn't look like a hack job. If it's a curve, do your best to draw the best curve that you can. So like for this one, again, using this example, this is not a straight line. The data curves is a good example of that. So you do your best to draw the curved line versus this one, use a ruler, okay? A couple other notes. You may be asked to interpret your graph, your data, so you need to look at it and examine what's going on. Just to make a note that abrupt changes often tell you something significant has happened, and if you see a discontinuity, examine what may have happened. So as an example here, okay, there's some things I like about this graph, there's some things I don't, okay? I don't like that there's not a title. If we were to title it, would be the dependence of population on time, okay, versus time. I don't like that there's not units, time, and again, what? Minutes, seconds, hours, days, weeks, and then population in hundreds, thousands, millions. We don't know, so it's unclear. However, if you know something about New Orleans and time, okay, if you remember Hurricane Katrina happened, all right, probably a lot of people either left the area or died, unfortunately, and this change is communicating something to whoever this graph is, you know, displaying information to. But you could make an inference about it, even if you didn't know about Hurricane Katrina or something, that you could say, okay, something occurred at this point in time. It caused a massive decrease in the population of New Orleans, and it's slowly been recovering. And depending on how much time has passed, it could also mean stuff is this minutes? Is it seconds? Is it a century? We don't know, so it's hard to make a really thorough analysis, but you could make one. So I want to make sure I give you examples of graphs that would meet all the qualifications that I'm giving you. So here is an example of what I would consider a graph that meets all of the requirements that I've outlined. So it has the title, the dependence of density of a liquid versus temperature. Okay, so this tells us that density should be the y-axis, and it is, versus temperature should be our x-axis, which it is. They also have units. Density is in grams per milliliter, and temperature is in degrees Celsius. Okay, degrees Celsius. Now, it doesn't start at 0, 0. Notice the origin starts at 15 for your x and 2.5. That's because the temperature, 15 degrees Celsius, is about 60 degrees Fahrenheit. Okay, if you're not familiar with that kind of conversion. And so this was like, you know, warm water. It wasn't cold water. It wasn't at 0. And the density didn't start at 0. Okay. And so this data, okay, has a range of the x-axis is pretty narrow. It starts at 2.5 and goes to 3.6. You could probably have even made it smaller, but it's filling the space quite nicely. And the temperature starts from 15 and goes to 85 because it ends around 80. So again, this is filling the space based on the data that was collected, and the origins starting appropriately, again, based on the data. I can't emphasize that enough. So a quick little summary. Doesn't have everything, but it's a good little summary slide. Your graph should be titled, both axes labeled with quantity and dimension, so units. You need appropriate scales used on both axes, and that the graph accurately represents data using a best fit curve when appropriate, or line. So this one, this is a curve. I mean, again, it's best judgment here. It looks like the data is kind of slowly increasing, and then it's becoming more exponential. So a line would probably look kind of awkward here. A curve looks better. Again, that's kind of a best judgment. This one, if you can kind of see, it says plot of speed versus time. So speed should be the y-axis, time on the x, which it is. They both have units, and it's scaled appropriately. So I hope this helps you in making graphs for chemistry class this year.